What if everything you thought you knew about empty space was wrong? Picture the vast, silent cosmos, a seemingly endless void between stars and galaxies. For centuries, we've imagined it as the ultimate emptiness, a perfect nothingness. But what if the truth is far stranger? What if the vacuum of space isn't empty at all? Beneath that calm, dark surface lies a hidden world teeming with energy, structure, and secrets that defy our everyday intuition. The great physicist Richard Feynman once said, "There's plenty of room at the bottom," and he wasn't just talking about the tiny. He was hinting at the invisible frenzy lurking beneath what we call nothing. Modern physics has peeled back the curtain on this cosmic illusion, revealing a reality that feels more like science fiction than science. The vacuum of space, it turns out, is alive with quantum fluctuations, particles and antiparticles flickering in and out of existence in a dance so fast, it's as if the universe itself is breathing. Fields we can't see permeate every inch of the cosmos, shaping everything from the mass of atoms to the fate of galaxies. Even the darkness between stars hums with a hidden energy, a force so mysterious it's accelerating the expansion of the universe itself. This isn't just empty space, it's a stage where the most fundamental laws of reality play out in ways we're only beginning to understand. So buckle up, because we're about to dive into the secret architecture of the vacuum. From ghostly virtual particles to the enigmatic Higgs field, from the turbulent quantum foam to the mind-bending possibility of vacuum decay, we'll explore how this so-called emptiness holds the keys to the universe's greatest mysteries. And it all starts with a question that will change how you see the cosmos forever. What if nothing isn't really nothing at all? The journey begins with the first clue, a phenomenon so bizarre, even physicists call it quantum foam. Ready to unravel the truth? Let's go. For thousands of years, we've stared up at the night sky and seen nothing but darkness between the stars, a void so complete it felt almost sacred in its emptiness. Ancient philosophers like Aristotle believed nature abhorred a vacuum, coining the term horror vacui to describe how space simply couldn't be truly empty. Even Isaac Newton, with his revolutionary laws of motion, imagined space as a static, unchanging stage, a blank canvas where celestial bodies moved but nothing else stirred. But what if this emptiness was the greatest trick the universe ever played on us? Picture standing on a beach at night, looking out at a perfectly calm ocean. The surface seems still, almost lifeless, but beneath those dark waters, a hidden world of currents, collisions, and ceaseless motion. That's exactly what modern physics has revealed about so-called empty space. The vacuum isn't empty, it's more like the surface of that ocean, masking an unimaginably complex world beneath. At scales smaller than atoms, particles wink in and out of existence faster than the blink of an eye. Fields we can't see or touch hum with energy, shaping everything from the spin of electrons to the expansion of the universe itself. The irony is staggering. The grand, silent expanse we call space is actually the most crowded place imaginable. Every cubic centimeter of what looks like nothing contains more activity than all the stars in the sky. Think about that next time you gaze up at the night. Those dark patches between constellations, they're not empty. They're seething with potential, vibrating with energy, alive in ways we're only beginning to understand. And the story of how we discovered this truth, how we went from believing in absolute emptiness to uncovering a quantum cosmos humming with hidden life, is one of science's most thrilling detective stories. It all started with a few bold minds questioning what everyone else took for granted. The moment you think you've grasped the quiet stillness of empty space, quantum physics steps in to reveal something astonishing. The vacuum is anything but still. Imagine a calm pond at midnight, its surface smooth as glass. Now zoom in 1,000,000 times, and suddenly that serene surface becomes a storm of tiny ripples, appearing and vanishing in the blink of an eye. That's the reality of quantum fluctuations, the first clue that so-called nothingness is actually a seething, dynamic arena where particles and their antimatter twins constantly emerge from the void, only to vanish again before we can even detect them. This isn't just theoretical speculation, it's a fundamental feature of the universe, baked into the very fabric of reality. At the quantum level, empty space isn't empty, it's a tempest of potential. Particles and antiparticles borrow energy from the vacuum itself, existing for fleeting instants before annihilating each other in bursts of pure energy. The rules of the game come from the Heisenberg uncertainty principle, which tells us that at these unimaginably small scales, energy can't be pinned down to a single value. Instead, it fluctuates wildly, and those fluctuations give rise to these ghostly particles. One of the most mind-bending proofs of this comes from something called the Casimir Effect. Picture two metal plates placed incredibly close together in a vacuum so close that only certain wavelengths of quantum fluctuations can fit between them. Outside the plates, fluctuations of all wavelengths are allowed, but inside, the options are limited. This imbalance creates a measurable force pushing the plates together, as if the vacuum itself were nudging them. It's not magic, it's the direct result of particles popping in and out of existence, and it's been confirmed in labs around the world. Physicist Paul Dirac once described this hidden layer of reality as a sea of energy, a phrase that captures just how far our intuition has to stretch to grasp it. Every cubic centimeter of space, no matter how empty, is filled with this roiling energy, a kind of cosmic background hum that underlies everything we see. And these fluctuations aren't just curiosities, they shape the universe in profound ways. Without them, stars wouldn't shine, atoms wouldn't hold together, and the very structure of space-time would be unrecognizable. So the next time you look up at the night sky and see the vast darkness between stars, remember, it's not a void. It's a stage where the tiniest ripples of energy dictate the fate of galaxies, where particles dance in and out of existence, and where the word nothing loses all meaning. And if that's not enough to make you question everything, just wait until you hear about the ghostly particles that make these fluctuations possible. If quantum fluctuations are the ripples in the cosmic pond, then virtual particles are the fleeting shadows they cast, ghostly visitors from a realm where the rules of ordinary physics no longer apply. These aren't particles in the traditional sense. They don't stick around long enough to be measured directly, vanishing almost as soon as they appear, like whispers in a crowded room. Yet their influence is everywhere. They're the unseen hands behind some of the universe's most fundamental forces, the invisible choreographers of reality's deepest dances. Take electromagnetism, for example. When two electrons repel each other, it's not some abstract field doing the work, it's virtual photons, particles of light that exist just long enough to carry that push between them. These phantom messengers pop into existence, deliver their cosmic memos, and disappear before anyone can catch them in the act. It's as if the universe runs on a network of tiny, temporary bridges, built and demolished in fractions of a nanosecond. The brilliant physicist Richard Feynman gave us a way to visualize this chaos with his famous diagrams, stick-figure sketches of particle interactions that look deceptively simple but contain entire universes of complexity. In these drawings, virtual particles appear as squiggly lines or loops, fleeting detours in the otherwise straightforward paths of real particles. They're the quantum world's way of cheating, borrowing energy for a split second to make the impossible possible. But here's where it gets even stranger. These ghosts don't just mediate forces, they leave fingerprints on the cosmos itself. The Lamb shift, a tiny wobble in the energy levels of hydrogen atoms, happens because virtual particles constantly buffet the electron, ever so slightly changing its dance around the nucleus. Even the very mass of particles, the thing that makes them something instead of nothing, is shaped by their fleeting interactions with virtual counterparts. It's as if reality itself is held together by an endless game of quantum peek-a-boo. And if that weren't mind-bending enough, consider this. The same virtual particles that operate on the scale of atoms might also be shaping the fate of galaxies. The energy they contribute to the vacuum isn't just a microscopic curiosity, it's part of the same cosmic equation that drives the expansion of the universe. So the next time you flip a light switch, remember, the spark that leaps to your finger is just the visible end of a chain reaction that stretches all the way down to the quantum void, where particles that barely exist make real the world we know. Even in the deepest freeze of absolute zero, where all classical motion grinds to a halt, the quantum universe refuses to sit still. This is the bizarre realm of zero-point energy, the leftover hum of existence that can never be silenced. Imagine turning down the volume on the cosmos until every star, every atom, every whisper of heat fades away. You'd still hear it, a faint, eternal vibration woven into the fabric of space itself. The Heisenberg uncertainty principle guarantees this restlessness, decreeing that particles can never fully settle into perfect stillness. If they did, we'd know both their position and momentum with absolute certainty, a violation of quantum law. So even in their lowest energy state, particles jitter with a kind of primordial energy, like a guitar string that never stops humming after the note fades. This isn't just theoretical poetry. Zero-point energy has teeth. It's the reason liquid helium defies gravity to creep up glass walls at temperatures near absolute zero, and why exotic materials can levitate above superconductors without explanation. Some scientists dream of tapping into this infinite reservoir. After all, a single cubic centimeter of pure vacuum may contain enough zero-point energy to boil every ocean on Earth. The catch, harnessing it would be like trying to bottle lightning with a sieve. The energy is everywhere, but it's locked in a form that resists extraction, like trying to grab hold of a shadow. That hasn't stopped visionaries from trying. From Nikola Tesla's cryptic notes to modern lab experiments with micro-scale Casimir effects, the quest to mine vacuum energy reads like science fiction. Some speculate advanced civilizations might already use it. Imagine spacecraft powered not by fuel, but by the faint tremors of empty space itself. Yet the challenges are cosmic in scale. Disturbing the vacuum's delicate balance could trigger catastrophic effects, like accidentally poking a hole in the universe's fabric. And then there's the math. Quantum field theory predicts vacuum energy should be unimaginably stronger than what we observe, leaving physicists with a discrepancy so vast it's called the worst theoretical prediction in history. So while zero-point energy remains tantalizingly out of reach, its implications ripple through reality. It shapes the stability of atoms, influences the expansion of the cosmos, and whispers a revolutionary truth. There's no such thing as true emptiness. Every void is a reservoir of untapped potential, humming with the energy of existence itself. And if we ever learn to listen closely enough, we might just hear the universe's deepest secret, that nothing truly is ever still. There's something unsettling happening to our universe, an invisible hand pulling at the seams of reality itself. We call it dark energy, and it's the greatest cosmic riddle of our time. Picture this: every galaxy, every star, every speck of dust in the cosmos isn't just drifting apart, it's being pushed apart at an ever-increasing speed, as if space itself were stretching like an infinite rubber band. What's bizarre is that this acceleration started relatively recently in cosmic terms, about 5 billion years ago, as if the universe suddenly decided to hit the gas pedal. This discovery turned physics upside down. Einstein had actually predicted something similar a century earlier with his cosmological constant, a mathematical fudge factor he added to keep the universe static, which he later called his greatest blunder. But where Einstein imagined this force maintaining balance, today's telescopes reveal something far stranger, an anti-gravity effect growing stronger as the universe expands. The leading suspect, quantum vacuum energy, the same seething sea of virtual particles we've been exploring. Here's the twist: if you calculate how much energy the vacuum should contain based on quantum theory, you get a number that's 10 to the power of 120 times too large. That's like predicting a teacup should hold all the water in the Pacific Ocean, a discrepancy so embarrassing physicists call it the vacuum catastrophe. The analogy that might help is imagining spacetime as a vast mattress with invisible springs. Normally, heavy objects like stars would create dips in the fabric, the way a bowling ball would dent a mattress. But dark energy behaves like springs embedded in the mattress itself, pushing everything apart with increasing force the more space stretches. What's wild is that this energy appears perfectly uniform, unlike matter clumping into galaxies. Dark energy seems to be a property of empty space itself, growing more dominant as the universe expands and becomes emptier. Yet for all we've learned, dark energy remains stubbornly mysterious. Is it truly constant, as Einstein's cosmological constant suggested? Or could it change over time, perhaps eventually tearing atoms apart in a big rip? Current telescopes can't yet detect variations in its strength, leaving us to wonder if we're seeing a fundamental feature of reality or just the first chapter of a deeper story. And here's the real kicker: if dark energy were slightly stronger, galaxies could never have formed. Slightly weaker, and the universe might have collapsed long ago. This perfect balancing act hints that we're either incredibly lucky, or that there are pieces of this puzzle we haven't even imagined yet. What's clear is that the vacuum of space isn't just humming with hidden activity, it's writing the future of everything. And as we peer deeper into the darkness between galaxies, we're left with a chilling possibility. The greatest force shaping our cosmic destiny might be the nothingness itself. Picture a universe where everything moves at the speed of light, where electrons zip around like cosmic race cars, never slowing down, never forming atoms, never building the matter that makes up stars, planets, or us. That was the baffling reality physicists faced until one revolutionary idea changed everything: the Higgs field. Imagine an invisible ocean filling every corner of the cosmos, even in the deepest vacuum. As particles swim through it, they experience drag not like friction, but as if the field itself is clinging to them, giving them the property we call mass. Without this cosmic molasses, the universe would be a featureless blur of light-speed chaos. The hunt for this field became one of science's greatest quests, culminating in a machine so colossal it could rival cathedrals, the Large Hadron Collider at CERN. In 2012, after decades of smashing protons together at nearly light speed, scientists finally detected its signature, the Higgs boson, a fleeting ripple in the field like a splash in that invisible ocean. This wasn't just another particle discovery. It was confirmation that space itself has texture, an underlying structure that dictates how matter behaves. Peter Higgs, the theorist who predicted it, reportedly cried when the news broke. What's astonishing is how pervasive this field is. Unlike magnetic or gravitational fields that weaken with distance, the Higgs field is always on, uniform across the cosmos. Even in the emptiest void between galaxies, it's there, silently shaping reality. Think of it like an unseen artist working behind the scenes. While gravity arranges planets and stars, the Higgs field determines the very weight of the paint they're made with. Some particles, like photons, glide through it effortlessly, remaining massless. Others, like quarks, trudge through like they're wading in syrup, becoming the building blocks of atoms. But here's the tantalizing question. If one invisible field shapes our universe so profoundly, could others be hiding in plain sight? The Higgs was once just a scribble on a theorist's notepad. Now it's as real as the ground beneath our feet. What other cosmic sculptors might be waiting in the void, their brushes poised to rewrite physics? The answer could lie in the whispers of particles we've yet to discover, or in the faint tremors of space itself, hinting at a reality far richer than we've dared to imagine. Down at the smallest scales imaginable, far beyond atoms, beyond even quarks, spacetime itself loses its smooth elegance and becomes a churning, frothing chaos. This is the quantum foam, the universe's ultimate basement level, where the very fabric of reality boils with uncertainty. Picture a stormy ocean seen from orbit, its waves reduced to a blur of motion. Now shrink that image a trillion times until each wave is smaller than a proton. At this scale, spacetime isn't a static stage. It's a seething foam where tiny wormholes twist into existence and vanish, where microscopic black holes flicker like bubbles in a cosmic soda, and where here and there lose all meaning. The idea traces back to John Wheeler, the physicist who coined the term in the 1950s. He realized that at the Planck length, a distance so small it's to a grain of sand, what that grain is to the entire observable universe, gravity and quantum mechanics collide in a frenzy. The smooth geometry Einstein described in his theory of relativity shatters into a probabilistic dance. Imagine trying to measure the surface of a bubbling pot with a ruler. At some point, the bubbles make the very idea of surface meaningless. That's spacetime in the quantum foam. Stephen Hawking took this further, suggesting these turbulent fluctuations might explain how black holes slowly leak energy, a phenomenon now called Hawking radiation. Near a black hole's event horizon, pairs of virtual particles pop up from the foam. Normally, they'd annihilate instantly, but if one falls into the black hole while the other escapes, the hole loses mass over time. It's as if the quantum foam is slowly erasing the universe's darkest objects from within. But here's where it gets truly unsettling. If spacetime is this chaotic at its core, what does that say about our everyday reality? The world we see is an illusion, a smoothed-out average of this underlying turbulence, like the calm surface of a lake hiding its molecular chaos. Some theories even suggest that wormholes in the foam could connect distant parts of the universe, or that time itself might stutter and loop at these scales. The problem, we'll likely never observe it directly. The Planck length is so tiny that probing it would require a particle accelerator the size of a galaxy. Yet the quantum foam's implications ripple outward. It hints at a universe built not on certainty but on probability and flux, a place where nothing and something blur into one. And if spacetime itself is this unstable at its foundation, what other layers of reality might we be missing? The answer could rewrite not just physics, but our very understanding of existence. Imagine two coins flipped simultaneously on opposite sides of the universe, landing with perfect correlation every single time, not by chance, but because some invisible thread binds their fates. This is the eerie reality of quantum entanglement, the vacuum's silent whisper linking particles across unimaginable distances. When two particles become entangled, their properties locked together in a cosmic dance, even if separated by billions of light years. Change the spin of one and the other instantly responds, as if space and time were mere suggestions. Einstein famously called this spooky action at a distance, a phrase that captures just how unsettling this phenomenon is to our classical intuition. The genius of physicist John Bell gave us a way to test this strangeness. His experiments, now known as Bell tests, forced nature to reveal its hand. Either particles were secretly communicating faster than light, a violation of relativity, or reality itself wasn't local, meaning objects aren't just influenced by their immediate surroundings. The results were unequivocal. Entanglement is real, and it defies our everyday notions of cause and effect. In labs around the world, scientists have replicated these experiments, sending entangled photons through fiber optic cables or even bouncing them off satellites, watching in awe as the particles maintain their ghostly connection. What's truly astonishing is how deeply this phenomenon might be woven into the fabric of the vacuum itself. Some theories suggest entanglement isn't just a property of particles, it's a fundamental feature of space-time, with the vacuum acting as a sort of cosmic switchboard connecting everything. Picture the universe as a vast network where entangled pairs form the threads of an invisible web, with the vacuum humming quietly beneath it all, enabling these instant correlations. This isn't just theoretical curiosity. Entanglement is the backbone of quantum technologies poised to revolutionize our world. Quantum communication, for instance, relies on entangled particles to create unhackable encryption keys. Any attempt to eavesdrop would disturb the delicate link, alerting the sender instantly. Quantum computers, meanwhile, leverage entanglement to perform calculations at speeds impossible for classical machines, solving problems like drug discovery or climate modeling in fractions of the time. Yet for all its promise, entanglement still holds profound mysteries. Why does the universe allow such connections? Is this a quirk of quantum mechanics or a hint of a deeper layer of reality we've yet to uncover? And if entanglement truly is the vacuum's hidden language, what else might it be silently orchestrating across the cosmos? The answers could rewrite not just physics, but our understanding of connection itself, proving once more that the void is anything but empty. Here's the thing about physics, it usually prides itself on precision. Calculate the charge of an electron, nailed it to 11 decimal places. Predict the existence of a new particle years before we detect it. Done. But when it comes to the energy of the vacuum, our theories face an embarrassment so colossal it's been called the worst prediction in the history of science. Imagine calculating the weight of a feather and getting an answer heavier than the entire observable universe. That's the scale of the vacuum catastrophe, a discrepancy not of a few percentage points, but of 120 orders of magnitude. The math seems straightforward. If virtual particles constantly flicker in and out of existence, their combined energy should give the vacuum a staggering density. Yet when we measure the actual energy driving the universe's expansion, dark energy, it's almost zero by comparison. It's like expecting a tsunami and finding barely a ripple. This isn't just a rounding error, it's a cosmic-sized clue that we're missing something fundamental. Physicists have scrambled for solutions, with one leading candidate being supersymmetry, an elegant theory proposing every known particle has a hidden superpartner. These shadow particles could cancel out the vacuum's predicted energy, like balancing a ledger with equal credits and debits. The catch, after decades of searching, colliders like the LHC have found no trace of these superpartners. Alternative explanations range from the mind-bending to the philosophical. Some suggest the vacuum's energy isn't constant but has decayed over time, like a cosmic battery slowly draining. Others propose we're seeing a statistical fluke, that our universe just happens to sit in a low-energy pocket of a multiverse where most regions boil with violent vacuum energy. Then there's the radical idea that gravity behaves differently at cosmic scales, masking the true energy density. Each theory has holes, but together they paint a thrilling picture. The vacuum isn't just hiding particles or fields, it might be hiding entirely new laws of physics. What makes this puzzle so tantalizing is its stakes. Resolving it could unlock secrets from the quantum realm to the fate of the cosmos. And until we do, the vacuum stands as both a humbling reminder of science's limits and an invitation to look deeper, question harder, and maybe, just maybe, find the keys to reality's next layer. Black holes aren't just cosmic vacuum cleaners, they're nature's ultimate laboratories for probing the extremes of empty space. Picture the edge of a black hole, where gravity warps space-time so severely that even light can't escape. Yet right at the boundary, something miraculous happens. The vacuum itself comes alive, birthing particles from pure nothingness. This is Hawking radiation, a phenomenon so counterintuitive it took Stephen Hawking's genius to reveal it. Here's how it works. Pairs of virtual particles constantly flicker in and out of existence near the event horizon. Normally, they'd annihilate instantly. But if one particle falls into the black hole while its twin escapes, the black hole loses a tiny bit of mass. Over eons, this slow leak causes even the mightiest black holes to evaporate, fading away like smoke in the wind. What's mind-blowing is that this radiation isn't coming from the black hole itself. It's being pulled from the quantum vacuum, a direct tap into the universe's hidden energy. The escaping particles carry away information about the black hole's temperature, which bizarrely gets hotter as the black hole shrinks. A stellar mass black hole might emit barely a whisper of radiation, colder than the cosmic microwave background. But a tiny, primordial black hole, it could glow fiercely before vanishing in a final burst of gamma rays. Yet this elegant process hides a paradox that keeps physicists up at night: the information loss problem. According to quantum mechanics, information can never be destroyed, yet if a black hole evaporates completely, what happens to all the data about the stars and gas it swallowed? Does it vanish forever, violating quantum laws, or is it somehow encoded in the Hawking radiation, like a cosmic SOS signal? This puzzle is so profound that solving it might require rewriting our understanding of reality itself. Black holes aren't alone in revealing the vacuum's secrets. Neutron stars, with magnetic fields trillions of times stronger than Earth's, can wrench virtual particles into reality, creating cascades of matter and antimatter. Even in empty intergalactic space, the vacuum flexes its muscles. Quantum fluctuations during cosmic inflation may have planted the seeds for all the galaxies we see today. From the darkest voids to the densest stars, the universe keeps whispering the same truth: there's no such thing as nothing. And as we push our instruments to new limits, who knows what other vacuum phenomena might emerge from the shadows? Picture the universe in its first moments, not the fiery chaos you might expect, but something even stranger: a vacuum humming with potential energy, poised to rewrite reality in a fraction of a second. This is cosmic inflation, the universe's ultimate growth spurt, where space itself expanded faster than light, doubling in size at least 60 times over in less than a trillionth of a second. What powered this mind-bending expansion? Not matter, not radiation, but the vacuum itself. A peculiar state called the false vacuum, where empty space was temporarily trapped in a high-energy configuration, like a ball balanced precariously on a hilltop. The false vacuum was unstable, and when it finally decayed, it released its pent-up energy in a cataclysmic transition, reheating the universe into the hot, dense plasma we recognize as the Big Bang. Think of it like a cosmic supercooled water bottle. Tap it just right, and it instantly freezes, releasing latent heat. That tap was likely a quantum fluctuation, a random flicker in the vacuum's energy that triggered the decay. The astonishing part, this process wasn't just explosive, it was meticulous. Inflation stretched quantum fluctuations from microscopic scales to cosmic proportions, imprinting them onto the fabric of spacetime. Those tiny ripples became the seeds for all the structure we see today: galaxies, clusters, and the vast cosmic web, like blowing up a snowflake to the size of a continent, and finding its delicate pattern now governs the shape of mountains. Evidence for this wild idea is etched into the oldest light we can see, the cosmic microwave background. The slight temperature variations in this afterglow match inflation's predictions with stunning precision, as if the universe left us a fingerprint from its first moments. But inflation doesn't just explain the universe's smoothness and structure, it hints at something even more radical. If space expanded exponentially once, could it happen elsewhere? The math suggests that inflation might not be a one-time event, but a perpetual process, with new universes bubbling up endlessly in a vast multiverse, each with its own laws of physics. This raises a haunting question. Was our Big Bang just one bubble among countless others, each born from its own false vacuum decay? If so, the vacuum isn't just the hidden scaffolding of our universe, it's the fertile ground for realities beyond our own, a cosmic nursery where universes are born, grow, and perhaps even collide. And if that's true, the deepest mysteries of existence might not lie in the stars above, but in the seething quantum depths of what we once called nothing. If our universe is just one bubble in an endless cosmic foam, each with its own unique laws of physics, then the vacuum isn't just humming with energy, it's an artist painting with an infinite palette. Picture a kaleidoscope the size of existence itself. Every twist creates a new configuration, a fresh universe where the vacuum's energy settles into a different state, birthing realities where gravity might be 1,000 times stronger, where light travels slower than sound, or where atoms never formed at all. This is the Multiverse Hypothesis, and it's not science fiction, it's a startling consequence of quantum field theory and cosmic inflation. The math behind this is both beautiful and bewildering. String theory, our most ambitious attempt to unify all physical laws, suggests the vacuum could stabilize in at least 10 to the power of 500 distinct configurations. That's a 1 followed by 500 zeros, more possible universes than atoms in our observable cosmos. Some might have conditions nearly identical to ours with slight tweaks. Maybe electrons are a fraction heavier, making chemistry unpredictable. Others could be so alien that matter as we know it can't exist, filled instead with exotic particles or forces we've never imagined. But how could we ever test such an extravagant idea? Scientists are hunting for cosmic fingerprints, subtle anomalies in the cosmic microwave background that might reveal collisions between our bubble universe and others. Others are simulating alternative physics in labs, creating tabletop universes where they can tweak fundamental constants. And then there's the eerie possibility that some of these parallel realities might leave traces in the quantum behavior of particles right here on Earth, as if the vacuum itself is whispering secrets from its other faces. The most humbling thought: if the multiverse is real, then every possible version of physics exists somewhere. Not just stars and planets, but realities where time flows backward, where dimensions curl in on themselves, or where the very concept of empty space means something entirely different. The vacuum, it seems, isn't just the foundation of our universe, it's the canvas for every universe that could ever be. And that raises a question more profound than any other. In this infinite cosmic gallery, why does this particular version of reality get to be ours? Imagine the universe as a frozen lake on a warm spring day. The ice seems solid, stable until somewhere beneath the surface, a single crack forms. That crack spreads faster than sound, shattering the entire lake in seconds. Now picture that same instability lurking in the vacuum itself, hidden beneath the apparent calm of empty space. This is vacuum decay, a scenario where our entire universe could cease to exist in the blink of an eye, rewritten by a single quantum event. Here's how it could happen. The vacuum we know might not be the lowest possible energy state. It could be metastable, like a ball resting on a ledge halfway down a hill. Given the right nudge, it could tumble into a deeper valley, a truer vacuum where the laws of physics themselves are different. If this transition began somewhere, perhaps triggered by a random quantum fluctuation or even a high-energy particle collision, it would create an expanding bubble of new vacuum, racing outward at the speed of light. Inside that bubble, fundamental constants might change. Gravity could reverse, quarks might dissolve, or time itself could stop flowing. The shockwave wouldn't just destroy matter, it would rewrite the very rules of existence, leaving no warning for those in its path. Before you panic, consider this: the odds are astronomically low. Our universe has lasted 13.8 billion years without collapsing, suggesting the vacuum is staggeringly stable. Physicists calculate the expected lifetime of our vacuum state to be longer than the current age of the universe by many orders of magnitude, but the sheer possibility raises profound questions. Could advanced civilizations have ways to detect impending vacuum decay? Might they even attempt to trigger it deliberately, like cosmic gardeners pruning unwanted branches of reality? While vacuum decay remains a chilling thought experiment, it underscores a humbling truth: that nothingness surrounding us holds unimaginable power. The same quantum fields that give particles mass and shape atoms could, under different conditions, unravel everything. Yet for all its apocalyptic potential, the vacuum offers safer wonders too, like the faint glow of particles appearing from nowhere, or the way empty space itself bends under gravity's touch. So while we ponder the universe's most dramatic endings, let's turn next to the quieter miracles hiding in the void. Among all the strange phenomena that reveal the vacuum's hidden energy, none is more tangible or more unsettling than the Casimir Effect. Picture two ultra-thin metal plates placed so close together they could almost touch, separated by a gap narrower than a wavelength of light. In ordinary circumstances, you'd expect nothing to happen, just two silent, motionless sheets in empty space. But in reality, they inch toward each other with invisible force, as if pulled by ghostly fingers. This isn't magic or some unseen glue, it's the vacuum itself pushing them together. A phenomenon first predicted by Dutch physicist Hendrik Casimir in 1948 and later confirmed in labs with stunning precision. Here's why it happens. Even in complete darkness, the space between those plates isn't truly empty. Quantum fluctuations create a chaotic sea of virtual particles popping in and out of existence, a jumble of wavelengths like an orchestra playing every possible note at once. But the plates act like cosmic gatekeepers, restricting which wavelengths can fit between them. Only fluctuations with wavelengths that perfectly match the gap's size are allowed inside, while outside, all wavelengths roam free. This imbalance creates a pressure difference, with more virtual particles pushing inward on the plate's outer surfaces than between them. The result: the plates are forced together by the weight of nothingness itself. The numbers are mind-bending. For plates separated by just 1 micrometer, about 100 times thinner than a human hair, the force equals roughly the weight of a single red blood cell. That might sound negligible, but at the nanoscale, where engineers build molecular machines and quantum sensors, this tiny push becomes a make or break factor. Modern nanotechnology harnesses the Casimir effect to design everything from frictionless gears in micro-electromechanical systems to ultra-sensitive detectors that could one day measure gravitational waves with unprecedented precision. Some researchers are even exploring ways to reverse the effect, engineering special metamaterials that could repel rather than attract, potentially creating quantum levitation devices. But the real magic of the Casimir effect lies in what it tells us about reality. This measurable force proves that the vacuum isn't passive, it's dynamic, responsive, and capable of exerting real influence on the physical world. It's as if the universe left us a breadcrumb trail, showing how the seemingly empty spaces around us are actually pulsing with untapped energy. And if we can measure the push of virtual particles between metal plates, what other vacuum phenomena might be waiting just beyond our current tools? Perhaps forces that bend light in unexpected ways, or whisper clues about the nature of dark energy itself. The void, it seems, still has secrets to share. If you could feel the universe's hidden energy not with a microscope or telescope, but with a rocket's throttle, you'd encounter the Unruh Effect. Picture this: an astronaut floating in what seems like perfect emptiness suddenly hits the accelerator, racing through the void at ever-increasing speeds. To everyone else, they're moving through a vacuum, but to the astronaut, something extraordinary happens. The once empty space around them begins to glow with heat, as if immersed in a warm bath of particles. This isn't an illusion or a sensor malfunction, it's a fundamental prediction of quantum field theory, where acceleration conjures particles from the apparent nothingness of the vacuum itself. The effect mirrors Hawking radiation in a fascinating way. Just as a black hole's gravity pulls virtual particles apart, creating real radiation, acceleration through space tears the vacuum's quantum fields, revealing particles where none existed before. The faster the acceleration, the hotter this phantom glow becomes. For a human astronaut, the temperatures would be imperceptibly faint. You'd need to accelerate at 1 trillion times the force of Earth's gravity just to detect a whisper of warmth. But theoretically, if you could survive such extreme motion, empty space would feel like an oven. Einstein's relativity tells us motion is relative. There's no universal rest frame. But the Unruh effect adds a quantum twist. An accelerating observer doesn't just experience different forces, they perceive an entirely different reality. Two people, one floating gently, the other racing ahead, would disagree on whether the vacuum is truly empty. This challenges our intuition about what's real, suggesting particles themselves might be observer-dependent, like cosmic mirages shifting with perspective. The implications ripple through modern physics. If acceleration creates particles, could the vibrations of atoms in a detector mimic this effect, producing noise that obscures delicate quantum measurements? Some theories even suggest that the Unruh effect might help bridge quantum mechanics and gravity, offering clues about how particles behave near black holes or in the early universe's violent expansion. Yet for all its theoretical elegance, the Unruh effect remains tantalizingly out of reach in the lab. The accelerations needed to produce measurable heat are beyond our current technology. Imagine a particle detector moving from 0 to light speed in a fraction of a second. But clever workarounds are emerging. Analog experiments using ultra-cold atoms or vibrating superconductors might soon simulate the effect, giving us a glimpse into how motion rewrites the vacuum's rules. What's clear is that the universe refuses to let nothing stay simple. Whether through gravity, acceleration, or sheer quantum stubbornness, the vacuum keeps revealing layers we never expected. And as we push toward mastering quantum technologies, these insights could prove vital, because if even motion can summon particles from the void, what other surprises might be hiding in the circuits of a quantum computer. Quantum computing doesn't just push the limits of technology, it dances on the edge of reality itself, where the vacuum's hidden chaos becomes both an obstacle and an ally. At the heart of every quantum computer are qubits, fragile packets of information that exist in superpositions of 0 and 1. Their power lies in this delicate balance, but here's the catch: their stability depends on shielding them from the noisy outside world. And one of the biggest sources of that noise, the vacuum's own restless energy. Virtual particles popping in and out of existence create tiny fluctuations in electromagnetic fields, nudging qubits out of their carefully prepared states like gusts of wind threatening to topple a house of cards. Engineers fight this quantum static with heroic precision. Superconducting qubits, the workhorses of companies like IBM and Google, are chilled to temperatures colder than deep space, where thermal noise fades but vacuum fluctuations remain. Error-correcting codes breakthroughs akin to cosmic spell checkers monitor qubits for mistakes and correct them on the fly, weaving redundancy into the quantum fabric. Some designs even exploit the vacuum's quirks intentionally, using squeezed states to redistribute quantum noise in ways that protect critical calculations. It's a bit like tuning a radio to cancel out static. By understanding the vacuum's rhythms, we can sometimes silence its disruptions. Yet the vacuum isn't just a foe to be tamed. It might hold the key to quantum computing's future. Topological qubits, a promising avenue pioneered by Microsoft, encode information in braided loops of quantum fields, where the twists themselves are protected by the vacuum's geometry. These structures are so robust that local disturbances like those from virtual particles can't easily unravel them, much like how a knotted rope resists fraying. And in labs worldwide, researchers are exploring vacuum engineering, sculpting electromagnetic fields to create quiet zones where qubits can thrive, turning the void's chaos into a tool rather than a trap. But beneath these technical feats lies a deeper question. What does it mean to build machines that rely on harnessing or outsmarting the vacuum's inherent unpredictability? Quantum computers don't just calculate, they exploit the blurry edges of reality where particles exist in multiple states until measured, and where emptiness teems with hidden activity. In that sense, every qubit is a tiny rebellion against classical physics, a proof that the universe's most fundamental layer isn't tidy or silent, but vibrant, restless, and rich with possibility. And if we can learn to navigate that turbulence, what other secrets might the vacuum surrender? Perhaps the answers lie not in circuits or code, but in the philosophical frontier where physics meets the nature of existence itself. Long before quantum physics gave us equations to describe the vacuum's hidden energy, human minds grappled with the paradox of nothingness in startlingly similar ways. Ancient Buddhist philosophers spoke of sunyata, the concept that reality is fundamentally empty of inherent existence, a vast interconnected web where objects have no independent nature. Meanwhile, across the world, Greek atomists like Democritus argued the opposite, that the universe was built from indivisible particles dancing through true void, like dust motes in a sunbeam. These two visions, one seeing emptiness as the ultimate reality, the other as mere backdrop, echo today in our struggle to define the quantum vacuum. Is it a thing brimming with fields and particles, or the absence we mistakenly label as nothing? Modern physics blurs this ancient boundary. John Archibald Wheeler, the visionary behind terms like quantum foam, proposed reality might arise from information itself, his famous it-from-bit hypothesis. In this view, the vacuum isn't just seething with particles but with potential, a cosmic hard drive where every fluctuation encodes bits of existence. Picture a vast, invisible ocean where waves aren't water but probabilities, where what we call empty space is actually a field of unresolved possibilities, constantly collapsing into the particles we observe. This turns the philosophical debate on its head. The vacuum isn't just a container for reality. It might be the source code, yet the mystery deepens when we ask why the vacuum exists at all. Some theories suggest it's a frozen relic of the early universe's symmetries breaking, like a lake freezing into ice with trapped bubbles of its liquid past. Others propose it's a dynamic medium, evolving over cosmic time. The unsettling truth: we still don't know if the vacuum's energy is a permanent feature of reality or a temporary phase in a larger cycle, like mistaking the calm eye of a hurricane for permanent stillness. What unites these perspectives is the vacuum's refusal to fit neat categories. It's not just stuff or not stuff, it's the stage and the actors, the silence and the song. And as we turn from philosophy to experiment, we're left with one haunting question. If the vacuum is this strange in theory, what will we find when we probe it directly? The answers might not just redefine emptiness, they could rewrite existence itself. The quietest place on Earth isn't a remote cave or a soundproof chamber. It's the heart of LIGO, the Laser Interferometer Gravitational Wave Observatory, where scientists listen for whispers from colliding black holes. But what's truly astonishing is what they've discovered lurking beneath even those cosmic ripples, the faint tremors of the vacuum itself. LIGO 4-kilometer-long arms aren't just sensitive enough to detect space-time bending by less than 1,000th the width of a proton. They've also glimpsed the quantum noise seething in empty space. Every photon bouncing between those mirrors carries traces of vacuum fluctuations, tiny jitters that reveal how nothingness thrums with hidden energy. To combat this quantum static, physicists employ a dazzling trick called squeezed light. Imagine trying to measure a feather's weight on a scale battered by ocean waves. Squeezing light is like redirecting those waves, redistributing quantum noise so it wreaks less havoc on specific measurements. By manipulating photons in states so delicate they'd vanish if you blinked, researchers can effectively quiet one aspect of the vacuum's noise while amplifying another. It's not silencing the void, it's tuning it, like a pianist softening the bass notes to highlight a melody. This technique isn't just theoretical, it's already boosting LIGO precision and could soon revolutionize quantum encryption and microscopes that see inside living cells. Meanwhile, labs worldwide are pushing further, attempting to coax usable energy from the vacuum itself. In groundbreaking experiments, microscopic devices called quantum drums vibrate in sync with virtual particles, harvesting whispers of zero-point energy. Other teams use ultra-cold atoms to simulate cosmic inflation, watching as vacuum-like states spawn particles from nothingness. The most audacious efforts involve engineering the vacuum structure with metamaterials, exotic substances that bend light in ways nature never intended, potentially creating pockets where vacuum energy behaves unlike anywhere else in the universe. Yet these lab feats aren't just about bending physics to our will, they're windows into the cosmos. The same quantum noise LIGO battles may hold clues about dark energy's grip on the universe. Squeezed light techniques could one day help telescopes peer past the quantum fog of the early universe, while vacuum energy experiments might reveal why our cosmos didn't collapse instantly after the Big Bang. Every flicker of particles in a lab's magnetic trap, every tremor in a chilled quantum sensor, echoes processes that shaped galaxies. The void, it seems, isn't just a frontier for physicists, it's the hidden conductor of the cosmic symphony, its rhythms written into everything from the smallest atom to the fate of the universe itself. The fate of the cosmos might seem like the plot of a science fiction epic, but it's written in the subtle hum of the vacuum itself, every cubic centimeter of so-called empty space holds a whisper of energy that could decide whether the universe ends in ice, fire, or something even stranger. Scientists call these possible endings the Big Freeze, the Big Rip, and the Big Crunch, three dramatically different finales, all hinging on the vacuum's hidden properties. Let's start with the Big Freeze, the most likely scenario based on current data. Picture a universe where expansion never stops, where galaxies drift so far apart that their light can no longer reach one another. Stars burn out, black holes evaporate, and space itself grows colder and darker until even atoms begin to decay. It's not a violent end, but a slow fading, a cosmic sigh into nothingness. This fate is driven by dark energy, which we now know is linked to the vacuum's own energy. Recent measurements from telescopes like the James Webb and ISN's Euclid suggest dark energy's strength isn't weakening. If anything, it might be holding steady or even growing, dooming the universe to this eternal expansion. Then there's the Big Rip, a far more dramatic exit. If dark energy strengthens over time, it could eventually overpower gravity, electromagnetism, even the nuclear forces holding atoms together. First, galaxies would tear apart, then stars, then planets. Finally, in the last fraction of a second, atoms themselves would be shredded as space-time stretches faster than light can traverse it. The vacuum wouldn't just expand, it would win, reducing all of reality to disconnected particles unable to ever interact again. It's a terrifying thought, but not impossible. Some theories suggest certain vacuum states could lead to this runaway effect, turning the cosmos into a chaotic sea of lonely fragments. The Big Crunch offers a different finale, one where expansion reverses and the universe collapses back into a singularity. Imagine all the galaxies rushing toward one another, temperatures rising until molecules, then atoms, then quarks dissolve into a primordial soup. It's the opposite of the Big Bang, a cosmic reset button. For this to happen, dark energy would need to weaken dramatically, allowing gravity to take the reins. Yet observations of distant supernova and galaxy clusters keep pointing the other way, making the crunch the least likely of the three. But here's the twist. The vacuum's role in all this isn't just about energy density, it's about stability. If our vacuum is metastable, as some theories suggest, it could decay at any moment, rewriting the laws of physics in an instant. Even if that doesn't happen, the vacuum's behavior over billions of years will shape whether life can persist. In a Big Freeze scenario, intelligent civilizations might have eons to adapt, harnessing black holes for energy or engineering new forms of existence. A Big Rip leaves no such luxury. It's a hard deadline no technology could evade. The chilling truth is that the universe's fate isn't just some distant abstraction. The same quantum fields that give particles mass and allow galaxies to form are also quietly steering the cosmos toward its ultimate destiny. And while we can't change that trajectory, understanding it might be the key to surviving as long as physics allows. After all, if the vacuum can shape the fate of galaxies, who's to say we can't learn to work within its rules, or even bend them to our will? Life as we know it isn't just a happy accident of chemistry. It's a fragile miracle balanced on the razor's edge of quantum stability. Every cell in your body, every strand of DNA, depends on the vacuum behaving exactly as it does. If the electron's mass were even slightly different, or if the strength of electromagnetism wavered by a fraction, molecules wouldn't form, proteins wouldn't fold, and life itself would be impossible. The vacuum isn't just empty space, it's the silent architect of biology, setting the rules that let carbon-based life emerge from chaos. But what if life doesn't just depend on the vacuum's stability? What if it actively harnesses its quantum quirks? Enter the Penrose-Hameroff theory of consciousness. one of the most provocative ideas in modern science. Physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed that our brains might exploit quantum processes deep inside neurons in structures called microtubules. These tiny protein filaments could, in theory, maintain quantum states long enough to perform computations like a biological quantum computer. The kicker: these quantum effects might rely on the vacuum's fluctuations, with consciousness emerging from the dance between neurons and the seething quantum foam beneath reality. It's a wild idea, and mainstream science remains skeptical, but if even partially true, it would mean your thoughts aren't just electrical sparks. They're quantum symphonies orchestrated by the hidden energy of the void. This isn't just speculation confined to labs and lecture halls. The vacuum's mysteries have captured imaginations far beyond physics, becoming a playground for storytellers and dreamers. From Star Trek's zero-point energy to the mind-bending tesseract in Interstellar, pop culture loves to riff on the idea that emptiness holds infinite potential. Marvel's Ant-Man shrinks between atoms by manipulating quantum realms, while video games like Destiny weave vacuum energy into their lore as a futuristic power source. Scientists might cringe at the artistic liberties, but these stories get one thing right: the vacuum isn't passive. It's a character in the universe's grand narrative, shaping everything from the cosmos to, just maybe, the flicker of thought inside your skull. So the next time you zone out daydreaming, consider this. You might be tapping into the same quantum whispers that fill the void between stars. And if that doesn't make you see nothingness in a whole new light, just wait until you hear how Hollywood spins these ideas into gold. Hollywood has never met a scientific concept it couldn't turn into a plot device, and the quantum vacuum is no exception. Star Trek's warp cores hum with zero-point energy, a fictionalized version of the vacuum's hidden power that fuels faster than light travel. Interstellar's tesseract, that mind-bending bookshelf behind the black hole, imagines higher dimensions folded into the void like cosmic origami. Even Marvel's Ant-Man shrinks between atoms by slipping into the quantum realm, a psychedelic micro-universe where time and space lose all meaning. These portrayals take wild liberties with physics. No, you can't extract limitless energy from empty space without violating thermodynamics. And no, falling into a black hole won't land you in your daughter's bedroom. But they get one thing profoundly right: the vacuum is anything but boring. What's fascinating is how often sci-fi stumbles into accidental truths. The idea of vacuum energy powering starships isn't pure fantasy. NASA Eagleworks lab once explored a controversial M-drive concept that, in theory, could harness quantum fluctuations for propulsion, though most physicists dismiss it as impossible. Interstellar's depiction of time dilation near Gargantua, the film's fictional black hole, was so accurate that physicist Kip Thorne published a paper on the visual effects. And while we can't manipulate gravity like the movie's characters, scientists are seriously studying negative energy states in the lab, exotic vacuum configurations that could, in principle, enable warp drives or traversable wormholes. Yet for every near-accurate nod to physics, there's a howler that makes scientists cringe. The vacuum of space doesn't freeze you instantly, it's a terrible conductor. And empty interstellar voids aren't swirling with visible energy fields. But here's the thing, these creative liberties matter less than the curiosity they spark. When Star Trek first mentioned zero-point energy in the 1960s, the term was obscure even among physicists. Now it's a staple of cutting-edge research and a gateway for audiences to ponder real quantum mysteries. The best sci-fi isn't a textbook, it's a spotlight pointing at the strangest corners of reality and whispering, "What if?" And that's exactly where our journey heads next, the unanswered questions that keep physicists awake at night. If the vacuum's energy is real, why is dark energy so weak compared to theoretical predictions? Could there be undiscovered fields lurking in the void, waiting to rewrite the laws of physics? And if the multiverse is real, are we just one bubble in a froth of universes, each with its own vacuum rules? Sci-fi's wildest ideas pale next to the genuine enigmas still hiding in plain sight, proof that when it comes to the vacuum, truth isn't just stranger than fiction. It's stranger than we've even imagined. For all we've uncovered about the quantum vacuum, the biggest mysteries are the ones still staring us in the face, questions so profound they could rewrite physics textbooks. First on the list, is dark energy really constant, or is it slowly changing over cosmic time? Right now, our best measurements suggest this mysterious force pushing the universe apart has remained steady for billions of years. But what if it's subtly strengthening or weakening? A shifting dark energy could mean our cosmos faces a very different fate than the cold, lonely big freeze we currently predict. Telescopes like the Dark Energy Spectroscopic Instrument are scanning millions of galaxies for clues, hunting for tiny variations that might reveal dark energy's true nature. Then there's the enigma of the vacuum's ground state, the lowest possible energy level empty space can reach. We know it's not zero, but is this the absolute bottom? Or could the vacuum suddenly drop to an even lower energy, rewriting reality in an instant? It's like wondering if the floor beneath your feet is solid bedrock or thin ice hiding unfathomable depths. Some theories suggest our vacuum might be metastable, balanced precariously between states, while others argue it's already at true rock bottom. The answer could determine whether vacuum decay remains a theoretical curiosity or a genuine cosmic threat. Perhaps the most glaring gap in modern physics is the chasm between quantum fields and gravity. Quantum mechanics flawlessly describes the subatomic world, while Einstein's relativity governs stars and galaxies, but these two frameworks refuse to play nice when it comes to the vacuum's energy. When we try calculating how much gravity the quantum vacuum should produce, the numbers explode to nonsense values, suggesting either our math is catastrophically wrong or we're missing something fundamental about how spacetime interacts with quantum fields. This isn't just academic navel-gazing. Cracking this code might explain why the universe didn't collapse under its own weight moments after the Big Bang. These aren't isolated puzzles, they're threads in a single grand tapestry. Dark energy's behavior could hint at undiscovered vacuum fields. The ground state question ties directly to theories of cosmic inflation. And solving quantum gravity might reveal why the vacuum's energy is so eerily fine-tuned for life. What's thrilling is how many tools we now have to probe these mysteries, from tabletop experiments creating synthetic vacuum states to gravitational wave detectors listening for quantum echoes in spacetime's fabric. Each unanswered question isn't just a blank spot on our map. It's an invitation to venture deeper into the quantum wilderness, where the next revelation might be hiding in plain sight. Future research is already charting bold paths forward. Next-generation atom interferometers could measure gravity's quantum effects directly. Space-based telescopes might catch dark energy in the act of evolving. And ambitious theories like string theory or loop quantum gravity continue refining their predictions, waiting for experiments to prove them right or wrong. The most exciting possibility that the solutions to these puzzles won't just fill gaps in our knowledge, they'll reveal layers of reality we haven't even dreamed of yet. After all, every time humanity has peered deeper into the vacuum, we've found not emptiness, but a mirror reflecting our own incomplete understanding of the cosmos. The next decade promises to peel back even more layers of the vacuum's mysteries, with experiments so precise they'd make Einstein's head spin. Leading the charge is LISA, the Laser Interferometer Space Antenna, a trio of spacecraft set to launch in the 2030s, forming a gravitational wave detector with arms millions of kilometers long. Unlike Earth-bound observatories, LISA will float free from seismic noise, listening for ripples spawned by collisions between supermassive black holes and maybe even cosmic strings, hypothetical defects in spacetime's fabric. But here's the kicker. LISA sensitivity could also catch the faint hum of quantum fluctuations in the vacuum itself, like hearing individual raindrops in a thunderstorm. Every wobble in spacetime carries echoes of the void's hidden energy, and LISA might be the first instrument to tease them apart from the cosmic background. Meanwhile, beneath the Franco-Swiss border, CERN upgraded Large Hadron Collider is gearing up to smash protons with unprecedented energy. The high luminosity LHC, slated for 2029, won't just hunt new particles, it'll probe the vacuum's structure by recreating conditions a trillionth of a second after the Big Bang. One tantalizing target, hypothetical actions, ghostly particles that might be the missing link between quantum fields and dark matter. If they exist, they could reveal how the vacuum's energy sculpted the early universe. And then there's Fermilab's Quantum Chromodynamics QCD project, where physicists are simulating vacuum decay in supercooled plasma, watching for telltale bubbles of new physics that might rewrite our understanding of cosmic stability. But you don't need a billion-dollar lab to explore the vacuum's quirks. Citizen scientists are already contributing through projects like Quantum Moves, a game where players help optimize quantum algorithms by manipulating virtual atoms. Home experiments like building a cloud chamber with dry ice and rubbing alcohol can reveal particle tracks from cosmic rays and even fleeting virtual pairs. Universities are crowdsourcing data analysis, letting anyone sift through telescope readings or particle collisions for anomalies. The vacuum isn't just a subject for elite researchers. It's a frontier where curiosity, armed with a smartphone or a DIY kit, can still make discoveries. What's thrilling is how these efforts, from space-based observatories to kitchen table science, converge on the same truth. The vacuum isn't passive. It's a dynamic, responsive entity that leaves fingerprints on everything from black hole mergers to the glow of a homemade particle detector. And as tools grow sharper, we're not just observing the void, we're learning to converse with it, one experiment at a time. You don't need a particle accelerator or a billion-dollar lab to catch glimpses of the vacuum's hidden activity. Some of its secrets can be uncovered right at your kitchen table. Take the humble cloud chamber, a DIY project that transforms a glass jar, some rubbing alcohol, and dry ice into a window onto the quantum world. When you set it up, trails suddenly appear like ghostly fingerprints, cosmic rays, and radioactive decay particles zipping through the alcohol vapor, leaving delicate condensation trails in their wake. But here's the magical part. Some of those streaks aren't just from passing muons or electrons. They're the brief, visible echoes of virtual particles, fleeting pairs born from the vacuum's energy, annihilating before your eyes. It's as if the void is whispering, "Here I am." For those who prefer screens to smoke trails, citizen science projects like Zooniverse's Muon Hunters or CERN LHC at home let anyone sift through real particle collision data, tagging anomalies or simulating quantum interactions on home computers. These aren't just glorified games. Volunteers have co-authored papers, helping identify rare events in datasets too vast for any single researcher to parse. Imagine spotting a collision pattern that hints at an undiscovered particle, or tracing energy spikes that could map to vacuum fluctuations. The frontier of quantum physics isn't locked behind lab doors. It's sprawled across your laptop, waiting for curious eyes. And if you're craving something more tactile, try this. Suspend two tiny metal plates. Aluminum foil works parallel to each other, spaced less than a hair's width apart. Shine a laser pointer on them and watch for subtle shifts in the reflected light. What you're seeing is a microscopic dance influenced by the Casimir Effect, the same vacuum force that nudges those plates together in professional labs. It won't win you a Nobel Prize, but it's a visceral reminder that the universe's hidden forces aren't abstract equations. They're tangible, measurable, and sometimes just a trip to the hardware store away. But beyond the thrill of detection, these experiments share something deeper. They reveal the vacuum not as a void, but as a living canvas. Every streak in a cloud chamber, every blip in a crowdsourced dataset, is a stroke in a masterpiece we're only beginning to appreciate. The same quantum chaos that molds galaxies also leaves traces in your basement. And that's the real magic. Not just that the vacuum is everywhere, but that its beauty isn't reserved for scientists in white coats. It's there for anyone willing to look closely, to tinker, to wonder, which brings us to the final, most poetic layer of all. How artists and poets have long sensed this truth, even before the equations caught up. Long before quantum physics revealed the vacuum's hidden energy, poets and painters sensed the profound truth that emptiness is never truly empty. Walt Whitman, in his Leaves of Grass, didn't just describe the night sky, he heard it humming as if the void itself were alive with unseen music. The vast similitude spans all, he wrote, capturing the same interconnectedness that modern physicists now trace to quantum entanglement and fields. Meanwhile, artist Yayoi Kusama transformed blank canvases into infinite universes with her infinity mirror rooms, where reflections stretch into endless depths, mirroring the fractal nature of space-time at the Planck scale. Her polka dots aren't just decoration, they're visual echoes of virtual particles, a cosmos where repetition births complexity from apparent nothingness. What's striking is how these creative visions parallel the revelations of science. When physicist Richard Feynman described the vacuum as a boiling sea of potential, he might as well have been channeling the romantic poets who saw nature as a dynamic, restless force. The Japanese concept of the artistic embrace of negative space, finds its counterpart in quantum field theory, where the gaps between particles thrum with invisible activity. Even the eerie stillness of a Mark Rothko painting, where color seems to vibrate against the void, mirrors the paradoxical tension of zero-point energy, a silence that's somehow full, a stillness that pulses with unseen motion. Yet there's a crucial difference. Where artists intuit the void's mystery through metaphor, physicists dissect it with equations. Kusama's installations evoke the vacuum's boundlessness emotionally, while LIGO interferometers measure its fluctuations to a precision of 1,000th of a proton's width. Whitman's cosmic awe needs no proof, but Higgs boson hunters spent decades and billions to confirm their vision. Both paths, one lyrical, one empirical, converge on the same revelation. What we call emptiness is a canvas for the sublime, whether framed by poetry or particle colliders. This duality invites us to see the vacuum not just as a scientific frontier, but as a cultural touchstone. From Zen gardens raked into perfect voids to the haunting silence in John Cage 4:33, humanity has always wrestled with the creative power of absence. Science now gives us a vocabulary for that intuition, revealing how the universe sculpts galaxies from quantum ripples and spins matter from fleeting vibrations. The void isn't a blank slate, it's the loom weaving reality's fabric, its threads as visible in a sonnet's pauses as in Feynman diagram's squiggles. And as we stand at the intersection of these perspectives, we're left with a question that bridges art and science. If the vacuum is this rich, this alive, what other wonders hide in plain sight, waiting for the right lens or the right poem? to bring them into focus. So what have we learned about this so-called emptiness we call the vacuum? Far from being blank or inert, it's the universe's most active construction site, a multilayered reality humming with invisible architecture. At the smallest scales, space-time itself churns like quantum foam, a turbulent sea where microscopic black holes and wormholes flicker in and out before we can blink. Zoom out slightly, and you'll find it saturated with fields, the Higgs giving particles mass, electromagnetic fields crackling with virtual photons, and perhaps others we've yet to discover. And permeating it all, a restless energy that refuses to quiet, from the zero-point vibrations that prevent absolute stillness to the dark energy stretching the cosmos itself. This hidden activity isn't just academic curiosity, it's the bedrock of existence. Without the vacuum's quantum fluctuations, atoms might never have clumped into stars. Without the Higgs field, electrons would zip through the cosmos at light speed, never forming molecules. Even gravity, the force that sculpts galaxies, emerges from spacetime's curvature, another feature of this dynamic void. The vacuum isn't just part of the universe, it is the universe, its patterns repeating from the spin of electrons to the dance of galaxy clusters. Yet for all we've uncovered, the vacuum remains physics' greatest teacher and trickster. Every answer spawns new questions. Why is dark energy so weak compared to predictions? Are there undiscovered fields waiting in the void? Could the vacuum's structure hint at deeper layers of reality? These aren't just gaps in knowledge, they're doorways. What's truly humbling is realizing how much we've underestimated nothingness. The ancient Greeks who feared a true vacuum, the medieval thinkers who called it God's empty space, they sensed a truth modern equations confirm: emptiness is full. Full of potential, full of mystery, full of the very codes that make reality possible. And as we stand on the brink of new discoveries, from quantum computers harnessing vacuum states to telescopes probing dark energy's evolution, we're left with a revelation as simple as it is profound. To understand the universe, we must first learn to see the wonder in the void. The deeper we probe the vacuum's secrets, the more we're confronted with a humbling truth. Our understanding of reality is like a candle flickering in a vast cosmic storm. Every discovery peels back another layer, revealing not simplicity, but greater complexity: quantum foam beneath particles, fields beneath forces, and now hints of multiverses beneath our own universe. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." And nowhere does this ring truer than in our exploration of the void. We've gone from seeing empty space as a passive stage to recognizing it as the most dynamic performer in existence, rewriting its script with every experiment we conduct. What makes this journey extraordinary isn't just the strange phenomena, it's how they force us to question the very nature of knowledge itself. The vacuum behaves differently for accelerating observers versus stationary ones. Its particle content changes based on how we look at it, and its energy appears to shape cosmic destiny while eluding our attempts to harness it. This isn't just physics, it's a masterclass in intellectual humility, reminding us that reality owes us no obligation to make sense by human standards. The 17th century scientists who first wrestled with vacuums would be astounded to see how their simple air pumps led to quantum fields and space-time foam, just as our descendants may one day laugh gently at what we currently consider cutting edge. Yet for all its mysteries, the vacuum isn't some alien abstraction. It's literally everywhere, including the space between these words and your eyes as you read them. That ubiquity makes its puzzles personal. When you breathe in, your lungs don't just fill with air, they inhale quantum fields. When you touch a table, the solidity you feel emerges from electromagnetic forces mediated by virtual particles. The vacuum's mysteries aren't distant curiosities. They're the hidden foundation of every sensation, every chemical reaction, every heartbeat. This brings us to science's great paradox. The more we illuminate the darkness, the vaster the unknown appears. For every question answered about dark energy or quantum fluctuations, a dozen new ones emerge. But that's not discouragement, it's an invitation. An invitation to stay curious, to keep questioning, and most importantly, to keep sharing these wonders. Which leads me to you, yes, you watching right now. What part of this quantum rabbit hole fascinates you most? Is it the potential of zero-point energy, the eerie connections of entanglement, or the terrifying beauty of vacuum decay? The conversation doesn't end here, it's just beginning. Your perspective might be the missing piece someone else needs to see the bigger picture. After all, the vacuum's greatest lesson might be this: nothing exists in isolation, not even ideas. If this journey through the quantum void has left you as awestruck as it's left me, don't let the conversation end here. Hit that like button if you're still reeling from the idea that nothing is everything, and subscribe to join us as we keep unraveling the universe's greatest enigmas. The vacuum's mysteries are far from solved, and your voice belongs in the discussion. Drop a comment below with your favorite head scratcher. Is it the eerie connectedness of quantum entanglement, the mind-bending potential of vacuum decay, or maybe the sheer audacity of dark energy's cosmic push? Let's geek out together. For those hungry to dive deeper, I've left links in the description to some game-changing reads. Start with The Quantum Vacuum by Peter Miloni for a masterclass on zero-point energy, or lose yourself in The Hidden Reality by Brian Greene for a tour of multiverse theories that'll warp your sense of scale. Prefer your physics with a side of wit? Quantum Physics for Poets by Leon Lederman and Christopher Hill makes the impossible feel intuitive. And if you're craving the latest research, search for papers on the Casimir Effect or vacuum fluctuations. You'll find treasure troves of cutting-edge experiments that read like sci-fi. This isn't just a goodbye, it's an invitation. Every click, every comment, every shared curiosity adds another thread to humanity's grand tapestry of discovery. So tell me, which vacuum mystery keeps you up at night? The answers we find next might just come from you. Until then, keep looking up, and remember, the emptiest spaces are always the most alive. Consider this: every atom in your body, every star in the sky, every whispered thought in your mind exists as a fleeting pattern in this boundless quantum sea. Our planet, that iconic pale blue dot, floats not in dead emptiness but in a vibrant, dynamic medium more alive than we ever imagined. The vacuum isn't just the backdrop of reality. It's the canvas and the paint, the stage and the actors, the silence and the symphony. From the quantum foam's chaotic flicker to dark energy's cosmic push, we've traced how this nothingness sculpts galaxies, births particles, and may one day decide the universe's fate. And yet, for all we've uncovered, the void remains the greatest teacher of humility. It whispers that our definitions of something and nothing are childish distinctions, that existence isn't a binary of presence and absence, but a spectrum of potential. The same quantum ripples that birthed galaxies course through your smartphone's circuits and the synapses of your brain. You aren't just observing the vacuum's mysteries, you're woven from them. So as we pull back to that cosmic perspective, Earth suspended in the velvet dark, remember this: the darkness isn't empty. It's a living thing, breathing with unseen energy, humming with fields we're only beginning to name. Carl Sagan's pale blue dot wasn't just a lesson in cosmic smallness, but a reminder of our radical connectedness. Every time you touch a table, catch sunlight on your skin, or gaze at the stars, you're feeling the vacuum's invisible hand at work. Now the screen fades, but the revelation lingers. The universe doesn't deal in emptiness, only possibilities. The credits roll. The room darkens, yet somewhere in the quantum depths beneath your floor, particles flicker in and out, whispering the same truth we've chased since the first time humans looked up and wondered about the dark. The vacuum isn't dead space. It never was. The vacuum is alive, fade to black.